Today marks a transition for us in this course. We're not only moving from Chapter 1 to Chapter 2, but sort of moving on to a new chapter in the course, in that we have spent most of our time up till now looking at deriving equations of motion and other things that are along those lines, linearization of the equations of motion, flexibility matrices, and things as that. Today, though, we're going to start talking about free response. We're going to be looking first here at single degree of freedom systems. Our standard form of the equation is going to be mx double dot plus c x dot plus kx is a 0. MCK may not actually be mass damping and stiffness components as such, but that will represent some form of that, and they are naturally occurring resulting from our derivation of equations of motion. The key part of this is that the equations of motion we're going to be solving in this course are linear. They will be equations with constant coefficients. M, C, and K will not be functions of time. And at this stage, we are looking at homogeneous equations, free response, no right-hand side. So with that, the very basic form of the solution of this is an exponential. Our goal here is to determine what that power is on the exponential. Those are going to end up being what we'll call the eigenvalues of the problem. So if I substitute that into the equation of motion, I get this. I will rule out the fact that x itself could possibly be a 0, because that would mean that x itself is a 0. So if I strike out that possibility, we're down to this second order polynomial here in lambda, which is known as the characteristic equation. It's a quadratic, so we can solve that. And so that solution takes place right here. And then we spend the next couple lines putting it in a slightly different form. That slightly different form is going to involve two parameters. One of a zeta, the damping, what's called the damping ratio, and the other one is omega n, which is the undamped natural frequency. So although the initial equation had m, c, and k as parameters, we really only need two. And the two that come out from this is a zeta and omega n. So how do we recognize that? Well, I think probably what you're going to be doing when you are faced with a single degree of freedom free response is you're going to take that equation. I'm going to move down to the bottom of the page where there's a little bit of white space. And from that equation of motion, you're going to divide through by the leading coefficient of m. Whatever happens to be in front of that, divide through by that, and you get x double dot plus c over m x dot plus k over m x is a 0. So consistent with the definitions that are shown above, this is what is ending up being the square of the undamped natural frequency. And this is what you will recognize as 2 zeta omega n. And that is how you will very likely be pulling off omega n and damping ratio from your equations of motion. But once you know that, then you know a lot about a character of the response. In particular, the damping ratio we see comes in right here. If the damping ratio is less than 1, your pair of eigenvalues are both going to be complex. There's going to be an imaginary part. Whereas if the damping ratio is larger than 1, they're both real. So we need to look at the size of the damping ratio in comparison to 1. What happens if the damping ratio is less than 1? In fact, put a star beside this, because this is the one that we're going to be looking at the most in this course. When the damping ratio is somewhere between 0 and 1, as I mentioned before, the roots become complex with imaginary parts. And so what we need to do when we put our solution together here, we need to be careful on how we handle that. So if I substitute those roots into there, you see I pull out the real part here. And what's left here are these complex exponentials. The way that we handle those is through the Euler identity. And the Euler identity says if you have an exponential of an imaginary power here, that's going to be cosine of theta plus or minus I sine of theta. And you'll see that that's exactly what we've used in writing down this next line. The rest of it is just combining coefficients together to get down to our final form. And our final form shows us the truth. And the truth here is that the the form of the solution for the underdamped case, the damping ratio less than 1, is we have a decaying exponential in front of a cosine and sine, where the frequency of the cosine and sine is given by omega n times 1 minus zeta squared. So that's the response. That's the description. Decaying exponentials multiplying cosines and sines. On the next page is a summary of what we have for the whole range of possibilities for damping ratios, ranging from zeta equal to 0 up to something larger than 1. We're going to lump these two together throughout this course. This is where we're going to be spending most of our time. Whereas the undamped case here is really just a special form of the underdamped. The decaying exponentials go to 1. How do we find these coefficients of C and S for the underdamped case? Well, it's very much like what we have here in general. In general, we'll take these combinations of these fundamental solutions of U and T, which are listed here. And the formal processes right here, we solve for what A and B are. But let's do it in particular for the underdamped case, for the damping ratio between 0 and 1. We saw that the solution form, x of t, is equal to the exponential e minus zeta omega nt c cosine omega dt plus s sine omega dt. What we need to do is enforce an initial displacement. So the initial displacement shows that the exponential goes to a 1. Cosine of 0 also goes to 1. Sine of 0 goes to 0. So what we find here is that C takes on the value of the initial value there for x. So that's the easy one of the two. The second one, we actually have to do a differentiation of this thing here. We got one function times another. Need to use the product rule. So minus zeta omega n e minus zeta omega nt times the bracketed term. And then I take the exponential times the derivative of the bracketed term. So that's going to be minus c omega d sine omega dt plus the response coefficient s times omega d times cosine omega dt. And so whenever I evaluate x dot, this should be a dot here, evaluate the x dot at time equal to a 0, we see that the exponential, that becomes a 1, the cosine becomes a 1, sine becomes a 0, exponential becomes a 1, sine becomes a 0, cosine becomes a 1. So what we're left with here is the minus zeta omega n times c plus s omega d and that's equal to the initial condition for x dot. From this, we want to solve for s, of course. So s then is going to be x dot initial plus the damping ratio omega n times c. C was x naught, and divide that by omega d. So these are the response coefficients that we have, s and c. This is how you go about finding that. The rest of the material in this section, we talk about something called the logarithmic decrement and how we can extract estimations for damping ratios. Definitely read through that. And then there are 3 examples in this section, examples 1, 2, and 3. Videos for the solutions for those are found on the blog. You need to go through those, each one of those. Each one of them has a particular point that I would like to make here in the course. So your lecture for today, we've just gone through that. You now need to look at the 3 examples, and we're all set. And we'll see you on Monday when we all return to class for next week.